In this video, we will introduce the backpropagation algorithm to train neural networks, and we will apply it to a two-layer multi-layer perceptron. For this, we will use the previously discussed chain rule and trace the influence of our model's weights on our loss function. So let's get started. Calculating gradients with backpropagation. Remember the information flow in a multi-layer perceptron, where the information flows from the inputs to the outputs. Once we've completed this forward pass, we do a prediction. In this case, let's say we do classification. We then measure the accuracy of our prediction using some loss function. So this loss function will use the true labels in order to calculate how accurate the predictions of our network are. Now in the backward pass, we're interested in this following question. How do we need to change all the individual weights in a neural network in order to bring down the loss function? So the relationship of the change in the loss with respect to change in each and every single individual weights is captured by the gradient of our loss L with respect to weight W. So this is the gradient of the loss with respect to some weight, and we have to calculate this quantity for each and every single weight in the network in order to know how to change this. So this will give us the direction which we need to adapt our weights in order to bring down the loss. Now the problem is that we cannot directly compute this in one single go because this is a big nested function. So if you remember, the network is composed of these individual layers which combine the inputs from before, and then they pass it through a nonlinearity, and this again goes through a combination of weights and nonlinearity. So it's this big nested function, and in order to really figure out how the change in each and every weight is related to the change in the loss function, we need to sort of peel back these layers and the nested function calculate the dependency and the gradient of the loss with respect to the outermost layers beforehand. So now let's see this with an example. So we need to propagate the information of the errors as we measured in the loss back through the network. So this is what is basically illustrated here. So this will go back all the way to the beginning. So this is what I mean by basically peeling back the layers. So as you can see by these red that is annotated here. And finally, we get to the input. So as we proceed from the last layer, go through these weights here and these units all the way back until we reach the input. Now we know how to individually change this in the network. Okay, so now we will take a look at how to calculate the gradients in the context of a simple example that is shown here. So let's assume that we have only one input X, and we combine this with weights W0 and a bias B0. Then this then goes into our pre-activation Z0, and we then pass this through our nonlinearity H0. So then the output of this is again combined with some weights W1, a bias B1 gets added, and this then goes into Z1. So now we have some activation function here again, and then we get our output Y hat, and Y hat then goes into our loss function L of Y hat. So just as we stated in the big picture view before, we want to know how to change the weights. And so how does the change in any of the weights and biases influence the loss? So this is expressed by the dependency of partial of L with respect to weight W. and partial of L with respect to the bias B. And we do this for all the weights and biases in the network. Okay, so let's look at how this works in detail. So the first thing that we need to do is the forward pass. And for the forward pass, we go from the bottom to the top. So it starts with basically an input X, which is then combined with weights and biases W naught and B naught to calculate Z naught. And this then gets passed through a nonlinearity G naught. And again, we will use this in the next layer in combination of the weights W1 and the bias B1 calculate Z1. And Z1 is again passed through some activation G1 here to give us our output Y hat. So that's the forward pass. Now let's calculate the backward pass. All right, here we work our way from the top to the bottom. So we start at the loss and calculate the partial of the loss with respect to the outputs of our network. So that's the outermost layer. So the loss, as we know, is directly dependent on our outputs. Once we have calculated the partial of L with respect to Y hat, we can then reuse this computation in order to go one step further backwards in this computational chain. Then we will reuse it here in the next step. So if we want to figure out the dependency of our loss L on the change in Z1, that is this quantity here, then this is expressed by the quantity of partial of L with respect to Z1. So now since L is not directly dependent on Z1, we'll have to use the chain rule and we'll go through Y hat. So we will go through Y hat here. So L is directly dependent on Y hat, and that's why we can reuse this quantity up here, and we have already calculated before. So we will multiply the partial of Y hat with respect to Z1. So we multiply the previously calculated quantity with the partial of Y hat with respect to Z1. So then what we have already calculated before, so we multiply with the partial of Y hat with respect to Z1. So this is then the outer function and this is the inner function. So we chain them together and this product then allows us to calculate the quantity of partial of L with respect to Z1. Now we need to go further and further back to calculate these quantities that describe the dependency of the loss on the change in each of the activations. Next, we will go one step further from Z1 and we will calculate partial of L with respect to the output of the first layer. So that's the partial of L with respect to H naught. Again, the loss is not directly dependent on H naught. So we need to go through the chain. So we have already calculated the quantity of partial of L with respect to Z1 in the previous step. So we will want to reuse that here. So that is now giving us the outer function again. And we need to chain it again with the inner function. So the inner function is then the partial of Z1 with respect to H naught. So we derive the input of the second neuron with respect to the output of the first neuron. So we quantified the change in Z1 when H0 is changed. Now we have this quantity here, partial of loss of L with respect to H0, and we can again use it in order to figure out the dependency one step further down the chain. So that is partial of L with respect to Z0. So partial of L with respect to Z0 is the dependency of the change of the loss with respect to the change in Z0. So just as we saw before, the dependency here is once again indirect with respect to H0, and we can reuse the result from before. So we will use this partial of L with respect to H0 here. And now what we have computed are these quantities, the partial of L with respect to Z1, partial of L with respect to H0, and the partial of L with respect to Z0. So we can now use these quantities to figure out how we need to change our weights. So far, this has only told us how to change the loss function, which relates to the change in activations. But what we are ultimately interested in is how the loss changes when we change our weights and biases. So that's what we're going to figure out in the next slide. Okay, so now we need to reuse the quantities that we have computed before. So to figure out the gradient of the loss with respect to the first weights, W1, we need the quantity that we have before here, that is partial of L with respect to C1, and we will reuse it in this computation. So the dependency of the loss on the weights W1 is through Z1. So Z1 is dependent on W1, and we will reuse this quantity partial of L with respect to Z1, and then we can chain it again with the derivative of Z1 with respect to W1. Okay, that was partial of L with respect to W1. So this tells us in which direction we need to change our weights W1. Now we also need to do the same for the bias here. So we will again reuse partial of L with respect to Z1, and then chain it with partial of Z1 with respect to the bias B1. So we will go through the partial of L with respect to Z1 here and chain it with partial of Z1 with respect to B1. So B1 also directly goes into Z1. So we need to do the same now again for partial of L with respect to W0. So if you realize that we are reusing these quantities that we have before, so now we will reuse partial of L with respect to Z0 that we computed here in this next step once again. And we will chain it again with partial of Z0 with respect to W0 here. Again, W0 goes into Z0. So this is the direct dependency here. So we also need to figure out how to change the bias B0. We will again go through the partial of L with respect to Z0. So we will want to reuse it here. And we will need to chain it again from the partial of Z0 with respect to B0 here. So this is the direct dependency. Okay, so now you've seen the full forward pass, which was up here, and the backward pass, which is down here. And you've seen to calculate the quantities that tells us how we need to change our weights and biases in order to bring down the losses. Okay, so this was all very abstract, so that was a bit on purpose. Let's now try to make this a little bit more concrete. So for that, we will need to actually define activation functions. So as you remember from the last week's lecture, there are a number of activation functions that we commonly use. So we will now denote the derivative of the activation function with respect to the activation as partial of h with respect to z, and we will also write this as h prime of z. That term now depends on which activation function we will use. So if we use a linear activation function, h prime of z will just be 1. And if we use a logistic sigmoid activation function, h prime of z will be h of z times 1 minus h of z. Or if we use the hyperbolic tangent sigmoid activation, h prime of z is 1 minus h of z squared. So now for an ReLU activation function. So before all these functions that we saw are smooth functions. So which means all of these are continuously differentiable. Now for a ReLU activation function, this is a bit more tricky. So ReLU is only piecewise differentiable. So we need to make a case distinction depending on the input of the function itself. So if the input is negative, then h prime of z will be 0. And if the negative of z, the slope is 0. So in the negative of z, the slope is 0. For the linear part, the slope is constant. So if we have a positive argument or 0, then h prime of z will basically be 1. So these are some examples of the derivatives of certain heavily used activation functions. All right, so now let's try to make this example more concrete. So we will consider the patterns x of n in our training set to do the forward pass. And we will put x of n and combine it with weights w naught and bias b naught. This then gives us z naught. So the first output activation h naught is then calculated by going through the activation g naught, and g naught here is an ReLU activation here. So in the output layer, we combine h naught with weights w1 and bias b1. So that gives us z1. And this then goes again into the activation g1, which is a linear activation function here. And this is why we get z1. So this gives us finally the output y hat. Now the output will again go into a loss function. So here we will consider a squared error loss, and this is 1 by 2 times of y hat minus y squared. Okay, so if we derive this squared loss function with respect to y hat, we get y hat minus y. So the derivative of the outer function cancels with the half, and the derivative of the inner function would be y hat minus y derived with respect to y hat, and that's just 1. So what we are left with is y hat minus y. Now we go back one step in the computational chain and we calculate the derivative of the loss with respect to the first pre-activation, which is z1. So the dependency of the loss on z1 through y hat. So now we first need to calculate partial of L with respect to y hat and then chain it with the partial of y hat with respect to z1. So we've already computed the partial of L with respect to y hat in this step above. So this is why we will reuse it here. So now we can reuse this calculation, and this is indicated by the green color. So the result of deriving y hat with respect to z1 is just 1. So this is because g1 is just a linear activation function. So this is the result of basically partial of L with respect to Z1. Now to figure out the change in weights W1, we need to calculate partial of L with respect to W1. So the dependency is indirect again. So we go through the chain that we already computed. So we will compute partial of L with respect to Z1. So this is what we computed before. So we computed partial of L with respect to Z1, and here Z1 depends on W1. So we chain this blue term that we've computed before with the partial of Z1 with respect to W1 here. So that gives us partial of L with respect to Z1 times H naught. So H naught here is a result of this term partial of Z1 with respect to W1 here. All right, so then we also want to know how we need to change our bias B1. So we will use this blue term partial of L with respect to Z1, and we will chain it again with partial of Z1 with respect to the bias here, because that one directly depends on the bias. So that gives us then partial of L with respect to Z1 times 1. And this is because if we derive Z1 with respect to B1, we just get 1 here. Okay, so let's now proceed backwards. So we want to calculate the dependency of the change in the loss on the change in the activation of the first neuron, which is H naught here. So we calculate partial of L with respect to H naught. Again, the dependency is through Z1 here, which we already computed. So we will chain it with the partial of Z1 with respect to H naught. So this partial of Z1 with respect to H naught is the partial of the input to the second neuron with respect to the output of the first neuron. So that dependency is through the weights W1. So then again, we get the partial of L with respect to Z1 times W1. So moving back further now, we calculate the partial of L with respect to Z0. So this dependency of the change in the loss with respect to the change in the input of the first neuron. So this dependency again goes through H0. So if you look at the computational graph, it becomes more clearer. So now we need to chain it with the partial of H0 with respect to Z0. So now this dependency of partial of H0 with respect to Z0 is through the activation function of the first neuron. So the activation function of the first neuron was ReLU activation. So now we again need to make the distinction by cases. So basically, if our input is positive, then we have 1 that we get, then partial of H0 by Z0. So we are left with this partial of L by H0 here on the right side. Then if the input is negative or 0, then this whole term here becomes 0. Okay, so now that we've figured out how to change in loss depends on the change in Z0, we're ready to compute how the loss changes when we change our weights W0 and bias B0. So we will reuse the cyan term from here, and which is partial of L with respect to Z0, and then Z0 is directly dependent on W0 here. So we will calculate the partial of Z0 with respect to W0. So this then gives us partial of L with respect to Z0 times X. Now for the bias, we do the same thing. So here we just need to input the term partial of z naught with respect to b naught, and the derivative of that then gives us 1 here. So that completes the full backward pass for this more concrete example with one linear output activation function and one ReLU activation function for the first neuron. So the backward pass allowed us to compute how we need to change the weights W1 and bias B1, as well as the weights W0 and the bias B0, so that the loss will also change. So we want the loss to go into the negative direction of the gradient in order to bring down the loss.
Okay, now let's very briefly discuss skip connections and how to accumulate the incoming derivatives if we have skip connections in addition to the forward connection. So here let's consider a 3-layer multi-layer perceptron as we see here. Now the red path connecting H0 to Z2 is now called as a skip connection, and this is because it skips over to the next layer. So if we have such a network, now during backpropagation to compute partial of L with respect to H0, we need to add the derivatives from both the forward connection and the skip connection. So here partial of L with respect to H0 now can be computed as partial of L with respect to Z2 times partial of L with respect to H0. Now this is the derivative computed from the skip connection, which is then added with partial of L with respect to Z1 times partial of Z1 with respect to H0, which is then the derivative computed from the forward connection.
So if we have all of the individual computations done, we can put everything together and give the generic learning algorithm for multi-layer perceptrons which use backpropagation. So for that, we will need to initialize our weight vector W and maybe some parameters. And these parameters are for the optimizer. So then we will have our while loop that is running while we are basically not converged. So we put in some criteria on the error and we loop over all the training examples in our data set D. We apply our input X to the network and do the forward pass. So we calculate the output and then feed it to our loss function together with our labels. Then in the backward pass, for each data point n, we want to calculate the partial of ln with respect to the weights and biases of the network. So after we are done with that, we sum over all the training patterns n for each gradient. So this gives us the quantities partial of L with respect to W and partial of L with respect to P for all the weights and biases. We then use the total gradients to perform one update step with our optimizer. So this approach is called learning by epoch. So we use the full training set in order to calculate the gradients for one update step. So this has the advantage that it gives rather accurate gradients, but the problem is that the update step will be rather few. So a different strategy is to take smaller batches. So these are called mini batches. So we take the mini batches of our training data and calculate the gradient on those. So this is a little bit more noisy maybe, but this enables us to do the updates much more quickly in the right direction. So this is what's done in practice, and we will see that later on. Now, in order to efficiently do that, we need to state this whole backpropagation rule in a matrix form. So in the matrix form, the backpropagation will be done very efficiently on modern GPUs, and that will be the topic of the next lecture. Okay, so again, I have two questions for you. What do the computed gradients represent? Why do we have to compute the gradients? So thank you, and I will see you in the next video.